Okay, so last time we looked at power series, in particular geometric power series, because those are relatively easy to get a handle on. And we were just trying to fit to A over 1 minus R. So we fix that center on R and then just try to get 1 minus, right? And then from there we can jump straight to our geometric series, sum A R to the n. So we could use that, we leverage that to derive some of our basic structures for power series representations of functions. Let's see, we got 1 over x was the sum n equal 0. This one we had to center at 1, right? Couldn't center it at 0. And that one had a flip-flop sign, right? So we got that one, 1 over x, centered at 1, which is nice. And we did 1 over 1 plus x and 1 over 1 minus x. The minus 1 just has the the plus 1, excuse me, just has the flip-flop signs, right? But 1 over 1 minus x, let's just do that one. That one's the simplest one on the series side, right? Because we already have a over 1 minus r. R is just x, so we just have x to the n here. And then substituting, if this was a plus, we just make it minus minus, and then we have the minus 1 to the n. So we had 1 over 1 plus x, sum n equals 0, negative 1 to the n, x to the n. Cool. So we've kind of already got those. We derive those from just using geometric series structure. Let's see. This one converges on, it's centered on 1, its radius is 1, it's convergent on 0, 2. These are both convergent on negative 1 to 1. Now, from these, what we're working on doing is deriving these basic structures so that we can get more complicated ones very easily, or relatively easy, without having to keep doing the work over and over and over again. So for example, well, let me give you the rules first, the properties. Let me leave, I'm going to leave this one here just for a moment, just to hang on to it. And let's say the series, or f of x is the series an x to the n, and g is the series bn x to the n. Okay, we'll just center at 0 just for convenience. If this is the case, if we do have these series representations of these functions, then f at kx, so if I want to find that function at some constant multiple, well, that's just my original function evaluated at kx. We just plug and chug, easy peasy. It's the sum an. So I'm going to plug in kx to the n, and we can do power over product just to make that a little nicer. We've got a sub n, k to the n, x to the n. So we can see that our sequence terms are there, a sub n, k to the n, and then we've got our x to the n's. Nice. So all we have to do is plug in, evaluate, and move. Likewise for powers. Let's say I want to know what that function is at some power of x, like f of x squared. Well, all I have to do is plug in to the series representation and evaluate. So it's the sum a sub n, x to the n to the n. Well, power to power, we multiply. So that's just a sub n, x to the n, n. we can combine them. So f of x plus or minus g of x is, well, we're just going to group stuff, right? We're adding two sums together. So I've got this a sub 0, a sub 1, a sub 2, x is, and then I'm adding b sub 0 plus b sub 1x plus b sub 2 x squared, and so on. So all I'm going to do is just group, right? I'll take a sub 0 and b sub 0 and say, okay, group those together. That's a sub 0 plus b sub 0. Then I'll look at the x terms. I'll say, oh, okay, it's a sub 1 plus b sub 1. I'm just grouping those, right? Then I look at the square terms and I go, well, that's a sub 2 plus b sub 2. Okay, so it's just grouping of addition. It's the sum a sub n plus or minus b sub n x to the n. Okay, now one thing to note is doing these operations can, and very often does, change the interval of convergence. So we do have to check, just to make sure what's going on. In particular, or for example, when we're adding or subtracting two power series representations, the interval of convergence is their intersection, right? So where f and g converge, then their sum or difference will converge. Okay, so those are some nice rules that we can use to derive more complicated function representations from some of these basic structures. For example, that's why I just left this one sitting here. Let's say we wanted to get let's say our function was 1 over 1 plus 3x cubed, say, for example. And I go, okay, well, I mean, I could have put like some multiple upstairs and that's fine. We can just pull it outside, right? But regardless, I look at this and I go, hey, that looks a lot like this structure. 1 plus 1 over x down here, right? I go, I'm just evaluating f, 1 over 1 plus x, at 3x cubed, right? So if, let me write it this way, if u is 3x cubed, then f of u is 1 over 1 plus u, right? So I've got the same structure. It's just that I'm evaluating at 3x cubed. So to get the power series representation, all I need to do is take my base structure here, which we have already, right? Series -1 to the n, and I just evaluate at 3x cubed. Then we can just do power over product and power of power and clean that up just to make it clear what our a sub n's are and what our x is. But otherwise, we're done here. We've already derived the series. We're just cleaning stuff up now. -1 to the n, 3 to the n, x to the 3n. Okay. So once we get those basic structures, deriving other more complicated ones is relatively easy. We just evaluate. Cool. Now, we got some properties and ways to derive ones from others, but we still have quite a few basic structures that we want to look at. We've done 1 over x and 1 over 1 plus and 1 minus x, because those we can handle with geometrics. But let's say we wanted to do like e to the x, or something like that. Well, there are sort of ways we can get around, but we got to get a foot in the door, and this is Taylor series. Actually, before we do that, let me give you one more property that's super useful for deriving other power series representations from base structure ones. If f of x is the series a sub n x to the n, then the derivative is, well, we can pull the constants out. We can always pull the constant out of a derivative anyway. So we have the sum. A sub n just sits there. It's, well, let's do it step by step just to make it clear. It's the derivative with respect to x of the sum of a sub n x to the n. Right? If these are equal, then if I take the derivative of the left-hand side, that should equal the derivative of the right-hand side. But the derivative of a sum is the sum of the derivatives, right? Derivatives are well behaved with respect to sums and differences. So I can pass that derivative inside. Okay? Right? The derivative of a sum is the sum of the derivatives. So that's okay to do. Now I can pull a constant outside of a derivative, and I could have pulled it outside of the sum anyway, and then pulled it outside of the derivative. So either way, all I'm doing is power rules, right? I'm just doing power rules. And even if that's x minus c, it doesn't matter, right? Because your chain rule, if this was, I'm being a little bit lazy just assuming that my center is 0, but it's not going to cause any problems, right? Because when I do my chain rule, the derivative of the inside is still just 1. So that's no problem, right? It's a linear function, leading coefficient of 1. Derivative of this is 0, so the derivative is just 1 when I do the chain. So it doesn't matter, right? We can do it in more general, but the same idea applies. We're just doing power rules now, okay? Sum a sub n, n x to the n minus 1. Booyah. Okay, so that's that. Sum a sub n x to the n minus 1. Long story short there, no, that's the function, not the derivative. Let me do that. Again, long story short is we're just doing power rules. There we go. The derivative is. Okay, and by the same argument, or similar argument, if f of x is equal to that series representation, then the integral of f is equal to the integral of that series representation. So integral of f of x dx is the integral of the sum of a sub n x to the n dx. But the integral of a sum is the sum of the integrals. So I can pass that through. Okay. Now I can pull a constant out of an integral. I could pull it out of the sum as well. Okay, and now we're just doing power rule. They're just power rules. X to the n plus 1 over n plus 1. Bam. Now, when we integrate, there is a constant of integration. So there is a plus c here. 9 times out of 10, a vast majority of the time, that c is 0. And all we need to do to find out what that c is evaluate at our center, right? So I'll take f at c and then evaluate the right-hand side. This stuff all goes away, right? Because we're evaluating at the center. So everything else will zero out and we'll be able to solve for c. It's just f at c, at the center, excuse me, not at the constant. Okay, so let's write that. Again, at the end of the day, long story short, we're just doing power rules. We got to worry about the constant of integration, but otherwise. Cool. Okay. So we can evaluate at constants, we can evaluate at powers of x's, we can take the derivative, they're just straight power rules at the end of the day, and likewise for integrals. Okay, so these are ways to derive other power series representations from ones that we know. Okay, cool. So, like I was saying, we need our foot in the door at some point. For things like, say, cosine or sine. These are transcendental functions, and our goal is to represent those as infinitely long polynomials, these power series representation. But we're not going to get those from geometrics, right? We can get like the arctan, for example, because we know that 1 over 1 plus x squared is the derivative. This is the derivative of the arctangent, right? So we can take 1 over 1 plus x, that base series, simply evaluate it at x squared, and then integrate. Those are all just straight power rules, right? Add 1, divide by the new power. So we can get arctangent from this base structure, for example, by doing a sequence of sub in whatever we need and then integrate or derivate whatever it might be. Okay. But how do we do it in general? How do we, let's say we can't fit to a geometric or make it from a known base sequence that we have already. It's not anything like 1 minus anything or 1 over 1 minus anything. So what do we do? Well, it goes like this. What we're going to do is we're going to say, okay, if there is this function representation, if f of x is the sum a sub n x minus c to the n, well, what does that mean? It means that f of x is a sub 0 plus a sub 1 x minus c plus a sub 2 x minus c squared plus a sub 3 x minus c, x minus c cube, and so on, right? I'm just writing out what that means. I go, okay, if that's the case, if f is equal to this power series representation, then their derivatives should also be equal. So let's look at the derivative. Well, derivative constant is 0. We're going to get 1. This will be to the 0 power, so we're going to get a sub 1 plus, we're going to get 2a sub 2 x minus c to the first power plus 3a sub 3 x minus c to the second power plus, let's just do one more term, we would get 4 a sub 4 x minus c cubed plus, and so on. Okay, great. So if that's the case, then this second derivative should also be equal. Now let's see, the derivative constant is 0. We're going to get 2a2 plus 3 times 2a3 x minus c plus 4 times 3 x minus c squared. Let's just do one more. We would have 5 times 4 x minus c cubed. Hopefully you're starting to see the pattern starting to see what's going on here. From these repeated power rules, we're getting that n factorial that's starting to pop out front, right? 3 times 2 times 1, 4 times 3, and then the next one will bring that derivative down, right? That power down. So 4 times 3 times 2 times 1, and here we're getting 5 times 4 times 3, and then the next one times 2. This is the factorial. Let's just do one more just for good measure. Third derivative. This is going to be gone. We're going to have 3 times 2 times 1 times a3 plus 4 times 3 times 2 x minus c plus 5 times 4 times 3 x minus c squared plus and so on, right? Nice. And for this will just keep going, right? Assuming that it's at least infinitely differentiable. It'll go forever, but like sine and cosine, those loop around in mod 4s, like groups of 4, things like that. Or, you know, e to the x is e to the x. So that's just going to always just be the same derivative all the time. Okay. Now, we'll say, what happens if I evaluate at the center? So here, I'm going to look at f evaluated at the center. And I'm going to go, okay, well, that zeroes out, that zeroes out, that zeroes out. Everything forever zeroes out, and I get a sub 0. Right? What I'm worried about here, my assumption was that the function was represented by this power series. I want all the derivatives to agree as well. So what's at stake is figuring out what are those a sub n's, right? The x minus c to the n, that's dummy. That's just part of the, that's the center, right? It's the a sub n's that we're worried about. What sequence of numbers do I need in order to make this true? So that's what we're doing right now, is we're figuring out, haha, well, f at c is this first a sub 0. Now, what happens if I take the first derivative? Now, the function itself is the 0th derivative. Okay. So the first derivative, evaluated at the center, let's look at that. First derivative, this is going to go, this is going to go, everything's going to go, and I'm going to get a sub 1. Okay. Second derivative, evaluated at the center. Here. This is all going to go, this is all going to go, this is all going to go, and I'm going to get 2a2. Third derivative, evaluated at the center. All this stuff zeroes out at forevermore, and I'm going to get 3 times 2, well, times 1, a3. Okay, and then on the next one, you can see what the pattern is now. F4, evaluated at the center, is going to be 4 times 3 times 2, a4. All right, and now we can solve for each of these. A2 is the second derivative evaluated at the center divided by 2. Really, that's 2 factorial, right? 2 times 1. The third is the third derivative evaluated at the center divided by 3 times 2 times 1, 3 factorial. The fourth coefficient is the fourth derivative evaluated at c divided by 4 times 3 times 2 times 1, which is 4 factorial. So we have a sub n is the nth derivative evaluated at the center divided by n factorial. There we've now solved for our coefficients. We figured out what coefficients we need in order to make the function agree with the series, the derivative, the second derivative, third derivative, and forever. Nice. And this is the formula for doing a Taylor series. This is how we derive the power series representation of some random given function. So our power series representation is the sum, n equals 0 to infinity. We have the nth derivative evaluated at the center divided by n factorial x minus c to the n. Now, if your center is 0, so we just have x to the n there, it's called a Maclaurin series. Taylor series is the more general idea. Okay. Nice. So let's try a quick one. Let's derive e to the x. That one's relatively easy. So let's say my function is e to the x. My Taylor series representation is nth derivative evaluated at the center divided by n factorial x minus the center to the n. So the x minus c to the n and the n factorial, that's just dummy stuff. That's coming from my formula. It's always going to be in there, right? What I'm concerned about is finding the numerators, the nth derivatives evaluated at the center. So that's our task. That's what we need to do. Say, okay, the 0th derivative is e to the x. So the 0th derivative, let's center this at 0. It's okay to do that. There's no discontinuities or anything. It's not going to blow up, or so just for convenience. We could center it anywhere we want to, but 0 makes life easy. The 0th derivative evaluated at 0, well, e to the 0 is 1. So the first derivative of x, the derivative of e to the x is e to the x. So the first derivative evaluated at 0 is e to the 0, which is 1. And it's going to be pretty obvious, right? Let's just do one more just to beat a dead horse here. The derivative of e to the x is e to the x. So evaluating at 0 is 1. Okay, clearly all those numerators are 1. All right. So we have the series n equals 0. All of the numerators are 1s. We chose to center at 0, so we just have x to the n over that n factorial, which is sitting right there. That is e to the x. Okay. Running short on time, but we've got e to the x now. If we want to get, well, no, here, we need the radius and interval of convergence for that. Yeah. All right, so we're looking at the limit as n goes to infinity, the absolute value of x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. So there's a sub n plus 1 over a sub n. That's the limit as n goes to infinity of the absolute value x to the n plus 1. This will flip up, n factorial over. This will go here, x to the n and n plus 1 factorial. Nice. So x to the n over x to the n, that's just 1. So I have x to the first power upstairs. n factorial over n plus 1 factorial, everything up to n is going to cancel out or become 1, and I'll be left with a single factor down here, just the n plus 1 left over. But the absolute value of x, as far as this limit is concerned, is a constant. What's moving in the limit is n. So x is just a constant. I can pull that outside. Well, the limit as n goes to infinity of 1 over n plus 1, that's clearly 0. Which is less than 1, right? We needed that criterion, the limit, to be less than 1 in order for this to converge. Well, regardless of what x is, that limit is 0, which is less than 1, so it converges for all x. The radius is infinity, negative infinity to infinity. It converges everywhere, which is really nice. We can pick any x, plug in, and it'll converge correctly. Okay, in the next video, we'll look at a few more examples. We'll derive some more basic structures using our Taylor polynomial.